Classical consumer theory relies on an unobservable foundation. It assumes that every choice is driven by a complete and transitive utility function, a mathematical map of a person's inner desires. But because we cannot peer into the mind, these preferences remain a theoretical primitive that we can never directly measure. Paul Samuelson inverted this logic. Instead of invisible desires, we start with what we can actually see: price vectors and chosen bundles. Taking this behavioral route means working backward, looking at scattered transactions to see if they reconcile with a rational consumer maximizing utility. This investigation reveals two significant hurdles. Local consistency in behavior is not enough to guarantee a globally coherent preference ordering. Furthermore, even when the data is perfectly consistent, it often leaves the consumer's true underlying preferences underdetermined. To build this model, we move from raw data toward a formal preference relation defined through affordability. If a consumer chooses bundle X over an affordable Y, they reveal a preference for X. To prevent direct reversals, we impose the weak axiom of revealed preference. WERP provides immediate local consistency, matching our basic intuition of what it means to be rational. However, it lacks the structural power to ensure those preferences remain stable across an entire market of complex choices. The strength of WERP depends entirely on the number of goods involved in the consumer's decision-making process. In a two-commodity space, budget lines are restrictive enough to prevent most preference chains from wandering. But as soon as a third good is introduced, local consistency is no longer enough to guarantee global rationalizability. In a 3D coordinate system, consider three bundles. First, X1 is chosen over an affordable X2. After a price shift, X2 is chosen over X3. Finally, despite X1 being cheaper, X3 is chosen over X1. This reveals strict preference cycles. If you examine these three observations pairwise, there is no violation. No two bundles ever directly contradict each other. WERP holds perfectly across the entire dataset. But when we look at the whole chain, coherence collapses. We have a cycle: X1 over X2, X2 over X3, and X3 over X1. Because the cycle contains a step of strict preference, no utility function can ever rationalize this behavior. The consumer has satisfied the local axiom, but failed the global test of rationality. To bridge this gap, we must move beyond pairwise comparisons. We need to enforce discipline across the entire transitive closure of the revealed preference network, ensuring that the logic holds up across long chains of comparison. This is the role of stronger requirements like the strong axiom, or SARP, and the generalized axiom, GARP. These axioms rule out the cycles that WERP misses.
GARP is particularly useful for finite data. It allows for indifference between bundles, but strictly forbids any cycle that includes a clear better than step. In traditional consumer theory, we use the Slutsky matrix, a grid of derivatives that tracks how demand for one good reacts to the price of another. For a consumer to be maximizing utility, this matrix must be symmetric. In our behavioral route, a cycle in the revealed preference graph is the exact mathematical counterpart to an asymmetric Slutsky matrix. Both indicate that the observed behavior lacks the structure required by utility maximization. Acyclicity functions as the structural constraint that links these discrete acts. By preventing the preference chain from looping, it ensures every choice can be interpreted as the output of a single, stable hierarchy of reasons. This leads us to Afriet's theorem. It proves that for any finite set of expenditure data, satisfying the acyclicity condition of GARP is both necessary and sufficient to prove the existence of a rationalizing utility function. This is a powerful empirical tool. It allows economists to test real-world data for utility consistency using a system of inequalities. We can check for rationalization without ever having to assume a specific, arbitrary functional form, like Cobb-Douglas. However, even a perfect pass on this test leads to the problem of underdetermination. While the data may prove that a rationalizing order exists, it cannot tell us which one is the true preference of the consumer. In any finite dataset, successful rationalization identifies an entire family of mathematically admissible utility functions. All of these distinct curves successfully validate the exact same set of observations, leaving the consumer's specific preference ordering partially identified. Because of this, applied researchers often use tools like Afriet's Critical Cost Efficiency Index. Instead of treating rationality as a simple pass or fail binary, this index grades the data, quantifying exactly how much a consumer would have to waste to make their choices consistent with utility maximization. Revealed preference theory does not perfectly unmask the consumer's inner utility. Instead, it provides a rigorous, bounds-based diagnostic, giving us the mathematical language to test our economic theories against the reality of human conduct.